crew. Real quick, want to do a little review on our VSEPR. That would be our valence shell electron pair repulsion. I know for some of us it's been a while, but we have seen this from our Chem 1 experience as we start looking at how we start to describe our covalently bonded molecules in three-dimensional space. Metals, pretty straightforward. They form these big delocalized sea of electrons. We sometimes call those amorphous because they're just kind of all right next to each other. Our ionic crystals, we know, form very orderly repeating lattice structures, and so their structure is pretty straightforward. Where we see the biggest variety and the biggest impact on those shapes and the impact from their arrangement is within our covalently bonded molecules. And so that's where our VSEPR, our, again, valence shell electron pair repulsion, becomes so very important to us about how we start to describe our arrangement of atoms in our molecules. Now, if you remember, there were a couple steps to this. Again, this is going to be a real brief review of our Chem 1 content when we start to think about how we start to draw our Lewis structures. Our first step is always going to be to count the total number of valence electrons available to us. So we start by kind of using the periodic table to count the total number of valence electrons. So as we're looking for a neutral atom, it's just whatever column it's in. So if we're looking at, for example, aluminum, we would count over its 3 columns. Aluminum has 3 valence electrons. If we count over to sulfur, it's in the 6th column. It's going to have 6 valence electrons. If you have an anion, you're going to add 2 additional electrons because it's got a negative charge. We add electrons in. Cations, we subtract. And again, I know you've got this, but it's just good to kind of revisit that as we go. When you go to start drawing your structure, you got to pick a central atom. Usually it's the first element of our compound as it's written. But when in doubt, never hydrogen. If you got a carbon, put it in the middle. Carbon can form 4 covalent bonds. Hydrogen can only form 1. Once you've got your central atom, you're going to make a single bond between it and all of the rest of your other atoms. Remember that each single bond consists of 2 bonding electrons. And then you're going to kind of arrange the rest of your electrons to satisfy your octet. You're going to fill everybody up so everybody's got 8. So start with your outer atoms. And then if you run out of electrons, that's when you're going to form your double or triple bonds, do a little extra sharing. And so from here, we can go back and check to make sure, have we used all of the valence electrons available to us? Do all of our atoms have an octet? The only one that would not need an octet would technically be hydrogen or helium, but we're never going to see any compounds with helium in them, so we're really only looking out for our hydrogen. Those are our steps for drawing our Lewis structures. Again, this is kind of brief as we start to look at our structures. And it helps, I think, to look at examples. Let's start off fairly straightforward. Let's start with, let's do methane. Sure, why not? Methane, we start by counting up our valence electrons. Methane, carbon's got 4 valence electrons. Each hydrogen has 1, so plus 1, plus 1, plus 1, plus 1. Or you could say plus 4 for all of those, for a total of 8 valence electrons. We've got 8 dots available for sticking our atom together. Now I pick central atom. Never hydrogen. Carbon's a good one. Cool. We got our carbon. We're going to bond to our outer atoms. In this case, our hydrogens. Keeping in mind that each single bond represents 2 electrons. And so sometimes some people will draw these in here. It's a little bit of extra work. But if it helps you visualize, at least early here in our process, it's not a bad idea to do it. With 2, 4, 6, 8, we've used all 8 electrons. We got 0 left, and so we've got, looks like everybody happy. Our hydrogens each are sharing 2, our carbons sharing 8. Here is our structure for methane. And then from the structure, we could then, if we wanted, go ahead and describe the shape. We're not quite there yet, but this is how we go about drawing our Lewis structures. So another example real quick. One that's maybe a little more involved in terms of looking at our pieces. What do we got? Let's do nitrogen trifluoride. I think that'll be a good one for us to kind of see these different rules. So nitrogen, if you count over, it's in the 5th column. So nitrogen's got 5 valence electrons. Each fluorine's got 7 times 3 is 21 for a total of 26 electrons total for our structure. Pick a central atom. When in doubt, go with the first one in your compound. We use single bonds to attach all of our outer atoms. And so if we are looking here, we've used 2, 4, 6. We got 20 left. Now I'm going to fill up our outside ones. I usually do dots. Some professors will do a line indicating 2 for each. It's just kind of personal preference. I usually just think it's easier to denote that these are lone pairs by doing the single dots. Does not matter. I just use 6. and 6 is 12, plus another 6 is 18. I got 2 left. If I've got extras, I'm going to put them on the center. If we look, this fluorine's got 8, 8, and 8, and our nitrogen has 8. We've got a stable Lewis structure. One more for you, just to show you all the different types of arrangements we could have. Let's do our diatomic nitrogen. We got 2 nitrogens. Each one's got 5 valence electrons for a total of 10 electrons all together. We've got central atom. Let's choose nitrogen. Sounds good. Single bond to our other nitrogen, we just used 2. We're down to 8. I'm going to fill up my outer one here. I just used 6 more. So I'm down to 2 electrons, and I've got those here. Problem, this nitrogen's got 8, but this one's only got 4. So we're going to take 2, bring them down, and do a double bond. So if you've got too few, we're going to do some extra sharing. This nitrogen still has 2, 4, 6, and 8. Now this nitrogen has 2, 4, and 6. Still not there. So we're going to take another 2, bring them down, make a triple bond. We can always double check. Sorry, I forgot to subtract out those 2. We had 10 electrons total. 2, 4, 6, 8, 10. Good. Nitrogen's got 8. Nitrogen's got 8. And it's this triple bond between our nitrogens that makes nitrogen so notoriously unreactive or stable. So that makes up like 80% of the room right now. Cool. Just a quick review on how we start to draw our Lewis structures. So now we can start to talk about the shapes that they make in our VSEPR molecules.